Awesome. So hi, everyone. My name is Vignav Ramesh, and I'll be taking the next 40 minutes or so to discuss interpretable natural language segmentation, or NLS, and generation, or NLG, based on linked grammar. So before we get into our INLS and INLG architectures, which will be the bulk of this presentation, I'd like to step back and look at the big picture that motivates our work. First is general conversational intelligence. GCI can be considered one of the core aspects of AGI, but there currently exists minimal overlap between the disciplines of AGI and natural language processing, or NLP. Only a few AGI architectures can comprehend and generate natural language, and most NLP systems rely on either hard-coded specialized rules and frameworks that can't generalize to the various complex domains of human language, or on heavily trained deep neural network models that cannot be interpreted, controlled, or made sense of. Moreover, the majority of AGI frameworks that do possess some level of natural language comprehension or understanding often cannot convey such knowledge in natural language without template-based customization or similar manual, labor-intensive procedures. The next motivation is, of course, INLP itself. To understand what INLP is, we have to start with XAI, or explainable AI. XAI requires the output of an AI model to be comprehensible to humans. Interpretable AI, or IAI, expands upon XAI by calling for an interpretable model or knowledge base, as well as explainable results. In other words, IAI gets rid of the black box model in AI. The extension of IAI to NLP is what we call INLP. As I'll explain later on, our architectures are two of the first INLP methods for NLS and NLG, and as such may bring a greater degree of GCI to proto-AGI NLP pipelines. Now for some more background. Current methods of grammar learning, such as deep neural networks or DNNs, require extensive supervised training on large corpora. However, humans are capable of acquiring explainable and reasonable rules of building sentences from words and segmenting sets of tokens solely based on grammatical rules and conversational patterns, and they clearly understand the grammatical and semantic categories of words. This raises the idea of unsupervised language learning, or ULL, which enables acquisition of language grammar from unlabeled text corpora programmatically in an unsupervised way. In a ULL system, the learned knowledge is stored in a human-readable and reasonable representation. Examples of ULL systems include the OpenCog AI platform's cognitive pipeline that enables unsupervised grammar learning, and Gluchenko et al.'s grammar induction technology that unsupervisedly learns grammar from only a single input corpus. The ULL pipeline consists of 5 main components: a text pre-cleaner, which pre-processes corpus files with configurable cleanup and normalization options; a sense pre-disambiguator, which performs word disambiguation and builds senses from tokens; a text parser, which parses sentences into word tokens or senses; a grammar learner, which learns word categories and rules from parses; and a tester that evaluates the quality of the inferred grammar. The ultimate output of the ULL pipeline is a model of the human language, and one such model is the linked grammar dictionary itself, which serves as a knowledge base behind our NLG and NLS architectures. So question answering, or QA, refers to the ability for machines to automatically answer questions posed in the form of human language. Let's take a look at this diagram here. An explainable QA pipeline involves components for both NLC, natural language comprehension, and NLG, natural language generation. During NLC, the question or input query is parsed and then semantically interpreted, which means the pipeline determines the underlying themes or topics of the question and then computes relationships between each component of the parsed query. During NLG, the query is then semantically executed. So the semantic relationships obtained during NLC are used to find the answer to the question. And finally, a formal grammar, such as linked grammar, is utilized to construct a grammatically valid sentence from words associated with the non-linguistic answer obtained in the query execution step. Linked grammar, or LG, is founded upon the idea that each word possesses a feature structure consisting of a set of typed connectors and disjuncts associating those connectors. Rules, which correspond to lexical entries or grammatical categories, describe a list of words and their set of defining disjuncts. Generation involves matching up connectors from one word with connectors from another, given the known set of disjuncts for both of them, while segmentation involves determining grammatical boundaries based on lack of disjunct connectability. A connector represents either the left or right half of a grammatical link of a given type, and different types of connectors are denoted by letters or pairs of letters, like S or SX. For instance, if a word A has the connector S+, this means that A can have an S link to its right. If a word B has the connector S-, this means that B can have an S link to its left. So in this case, if A occurs to the left of B in a sentence, then the two words can be joined together with an S link. The Link Grammar Dictionary, then, is a database that maps all common words of a given language to the connectors that define them. Disjuncts are sets of connectors that constitute the legal use of a given word. For instance, the word cat, shown here, has the expression D- and, in parentheses, S+ or O-, meaning it has two disjuncts, D- S+ and D- O-. Macros are single symbols that define large connector expressions. Essentially, they're a form of shorthand that are used throughout the Link Grammar Dictionary to reduce redundancy of connector expressions and increase readability. So in this example here, we have cat and snake are both assigned D- and S+ or O-. We can replace that entire connector expression with a macro called, for example, macro. And essentially, any time in the Link Grammar Dictionary that D- and S+ or O- appears, we can substitute the macro just in there to as a form of shorthand to improve readability. Okay. So in Link Grammar notation, a sentence is a set of tokens, words, punctuation, and other syntactic structures that may be linked by matching connectors between pairs of tokens. The rules of Link Grammar impose additional constraints beyond the matching of connectors, namely the planarity and connectivity meta rules. Planarity means that links don't cross, while connectivity means that the links and words of a sentence must form a connected graph. So all the words must be linked to the other words in the sentence via at least one path. Overall, the structure of grammatical knowledge as stored in Link Grammar appears interpretable, human readable, and maintainable, including the ability to add new rules and amend existing ones based on the intent of a human linguist maintaining the knowledge base, or a programmatic language learning framework, such as the ULL pipeline I discussed previously. Furthermore, unlike most alternative grammar rule dictionaries and APIs, such as Spatie and Universal Dependencies, or UD, LG does not require grammar rules to be hard-coded into client-side architectures. LG rules can also be learned dynamically through the ULL pipeline. So ultimately, these characteristics of LG allow our grammar induction algorithm to comprehend and process text under the premise of ULL, and thereby better serve as an INLP method for the purposes of the NLG and NLS tasks. So now let's dive into our NLS architecture. So natural language segmentation is the process of dividing written text into meaningful units, such as words, sentences, topics, or paragraphs. Text segmentation encompasses a variety of problems, such as word segmentation, intent segmentation, and so on. But our work is concerned with sentence segmentation. Sentence segmentation is the problem of dividing a string of natural language text into its component sentences. Note that we refer to sentence segmentation specifically in the context of separating bodies of text into valid sentences solely based on the grammatical relationships between individual words, meaning that we do not take into account punctuation, capitalization, or other syntactic structures. This allows our approach to generalize to various languages other than English, since not all written languages contain punctuation characters useful for approximating sentence boundaries. There are two primary sources of unsegmented text on which our NLS algorithm can operate: the text output from speech-to-text, or STT, recognition engines, which are often used to pre-process the inputs of voice-activated question answering or chatbot pipelines, and crawled web pages. STT engines transcribe audio content and return sequences of tokens without delimiters. Similarly, web scraping returns raw HTML and CSS output. The returned content often does not contain proper punctuation, and HTML or CSS tags are usually neither accurate nor consistent sentence boundary identifiers. In both these scenarios, our NLS architecture can be used to perform sentence segmentation without requiring the presence of delimiters. With regards to the QA pipeline, our work is concerned with both parsing the question as well as semantic query execution. While parsing the input query, Our NLS architecture can first separate the token sequence that represents the question into its component sentences, which can then be passed on to the semantic interpretation step. Semantic query execution matches relevant texts with the input query, often expressed as a set of keywords between which exist various semantic relationships. Given an NLP architecture that deals with the problem of matching the query with available documents, such as those available on the internet, we focus on segmenting these documents into their grammatically valid component sentences. A subset of these sentences most relevant to the input query can then be passed on to the relationship extraction and sentence construction steps of the NLG component of the question answering pipeline. Now on to the methodology behind our NLS architecture. As you can see in this diagram, there are two main components, loader and segment. Loader is a piece of utility infrastructure applicable to all architectures, including our NLG model that we'll discuss in a bit. The loader produces a dictionary object from a link grammar dictionary file. This dictionary can be used in a parser, which creates parses of sentences that can be used to process the input query during the first step of the question answering pipeline. Or it also feeds into segment, which is the core of our work. Loader loads and stores the link grammar database in various classes for future usage. Specifically, the dictionary class stores a list of word objects. Each word contains a unique rule object. A rule contains a list of disjuncts, and each disjunct object stores a list of connectors that constitute the legal use of the given word. Currently, the loader architecture only supports the English language and does not handle more complex morphological structures, including those needed to support languages such as Russian that require extensive morphology usage. As shown in the algorithm to the right, the makeDict function, which comprises the core of the loader, utilizes the information in an array of lines obtained from the link grammar database to create an array of dictionary objects that map each common word or phrase that link grammar supports to its associated rule. To do so, it extracts a link grammar rule from each element of the lines array, storing any new macros, remember those single links that define larger connector expressions, in the data structure called macros. The algorithm then replaces each macro with a rule with its expanded expression and assigns the modified rule to the word it defines. This mapping forms the dictionary objects that are then sent to the segment class. Given the dictionaries generated by loader, the segment class computes a segmentation for a string of text by first extracting the tokens, words, and punctuation from that text, and then clustering those tokens into valid sentences as per the segment function. The segment function loops through the input array called tokens and determines if certain subsets of tokens can form grammatically valid sentences via the connects function. Given a pair of consecutive tokens left and right, connects determines the lists of rules left list and right list that correspond with left and right, and then checks if any disjunct in any rule in left list matches with any disjunct in any rule in right list. If so, those two words can be marked as connectable, and the process continues for the next pair of tokens. Note that connects also works for groups of 3 or more tokens in certain grammatical scenarios where 2 consecutive tokens should not be linked. And we'll get into this in more detail when we discuss NLG. So our algorithm was tested on 2 distinct corpora. When tested on 88 sentences with words all part of SingularityNet's small world POC English corpus, our algorithm segmented the corpus text into 87 total sentences and achieved an accuracy of boundary identification of 97.7%. When tested on an excerpt of Lucy Maud Montgomery's Anne's House of Dreams, as found in the Gutenberg Children's Corpus, our algorithm accurately identified 7 of 9 sentence boundaries and segmented the text into 11 sentences, 1 sentence more than the ground truth. We compared our NLS architecture to 3 widely used open source sentence segmentation frameworks: Syntalk, PragmaticNet, and Deep Segment. Syntalk computes segmentations by recognizing terminal markers, which are syntactic structures, such as periods, exclamation marks, question marks, etc., that signify sentence boundaries. PragmaticNet is an unsupervised, opinionated, and conservative segmentation framework that, similar to Syntalk, segments text into sentences based on punctuation, quotations, and parentheticals. Both Syntalk and PragmaticNet identified 0 boundaries in the text from both the POC English and Gutenberg corpora, thereby returning 1 total sentence for each corpus and yielding an accuracy of 0%. Since Syntalk and PragmaticNet rely on punctuation and other syntactic structures for segmentation, they're unable to segment bodies of text without punctuation. Deep segment utilizes bidirectional long short-term memory networks in a conditional random field, or CRF, based supervised segmentation model aimed at segmenting unpunctuated bodies of text into sentences. Even though it does not rely on punctuation, deep segment still identified only one segmentation boundary in the POC English corpus and two boundaries in the Gutenberg corpus, all of which were accurate. So that yielded accuracies of 1.15% and 22.2%, respectively. So as you can see, our NLS architecture far exceeds these baselines, and most importantly, provides accurate support for unpunctuated bodies of text, thus generalizing to segmentation tasks across languages with varying syntactic structures. Our results were mainly affected by the issue of grammatical ambiguity, a problem whereby the same word can take on different roles in a sentence. For example, saw can take on both noun and verb forms, as shown here. Consider the string of text, dad has a hammer, mom has a hammer. It would be grammatically appropriate to segment this text into the two sentences, dad has a hammer and mom has a hammer, because the words hammer and mom can't be connected. However, this is only true for the noun form of hammer. The verb form of hammer can technically be linked to the object mom. The presence of these grammatically correct yet contextually wrong phrases decreased our sentence boundary identification accuracy. Semantic or word sense disambiguation, a solution to the grammatical ambiguity problem, determines which sense or definition of a word is activated by that word's use in a particular context. Current unsupervised semantic disambiguation methods include dictionary-based algorithms that utilize knowledge encoded in lexical resources to learn the senses of words. Implementing one such method will be part of our future work. Okay, so now let's move on to our NLG architecture. Natural language generation refers to the process of mapping some representation of data or information, usually non-linguistic, to a linguistic, grammatically and morphologically valid, representation of that information. The task of generating even simple sentences demands a large body of knowledge, grammatical, syntactical, morphological, phonological, etc. One possible way to build this knowledge base is to develop an integrated representation of semantic and grammatical knowledge, using an extended link grammar schema. However, while this may be a product of our future work, our current NLG architecture is concerned only with generating sentences using the basic link grammar database in its current form, so only grammatical knowledge. Our architecture focuses on the service realization component of NLG. Service realization refers to a determination of how the underlying content of a text, in the form of a list of words, should be mapped into a sequence of grammatically correct sentences. Often, the same content can be expressed in various sentential forms. An NLG system must first determine which of these sentential forms is most appropriate, and second, ensure that the resulting sentence is syntactically and morphologically correct. So, for an example, take the scenario of surface realization. We have the words the mouse, a cat caught, and that becomes a sentence, the cat caught a mouse. However, it is grammatically valid to also say the mouse caught a cat. It's just that contextually, it's more likely to say the cat caught the mouse than the mouse caught the cat. So that's why semantic disambiguation is important. You have to add context knowledge in addition to the grammatical knowledge. Our NLG work is concerned with the final part of the question answering pipeline. With link grammar serving as the requisite formal grammar, our NLG architecture automates sentence construction from the words derived in the penultimate part of the pipeline, and thereby enables question answering with minimal to no human interference. Once again, we use the loader as utility infrastructure for storing the link grammar database in memory. The generator then uses the dictionaries returned by the loader to perform surface realization. After obtaining the loaded dictionary objects from the loader, the generator determines what sentences can be formed from a given list of words via valid link grammar rules. First, given a list of those words, the generator determines a subset of all orderings of the words that satisfies initial checks of the planarity and connectivity meta rules. For example, one partial connectivity check that the generator implements involves ensuring that the first and last words are capable of forming links to the right and left, respectively. Then, for each ordering in the subset, the generator determines if that ordering is valid. Specifically, it ensures that every pair of consecutive words, with certain exceptions that I'll talk about in a second, can be connected via links, part of the dictionary objects. To do so, the generator uses the connects function, which operates in the same way as in the NLS architecture. So if you remember from the NLS part of the presentation, I mentioned that connects also works for groups of 3 or more tokens in certain grammatical scenarios, where 2 consecutive tokens should not be linked. As a motivating example, consider the link grammar parse of this sentence, is a human. We see that links are not between consecutive tokens, for example, is to a and a to human, but instead both is and a are linked to human. This is because a is a determiner, and thus it and the preceding verb must be linked to the object, human in this case. So the generator takes these exceptions into account when determining the connectability of tokens. Before we move on to the results of the generator, we have to define a few new metrics that we use to evaluate our architecture. In terms of canonical NLG metrics, we report 4 scores. First, the bigram variant of blue, a measure of the number of matching bigrams in 2 sentences. So for example, in the sentence, this is a sentence, we have 3 bigrams. This is a, and a sentence. Second is WVCS, or word-to-vec cosine similarity, calculated as the cosine of the angle between the vector encodings of the candidate and reference sentences. Third, WER, or word error rate, which is a measure of the edit distance between 2 sentences. WER is calculated as the number of substitutions plus the number of deletions plus the number of insertions needed to change the candidate sentence into the reference sentence, all over the number of words in the reference sentence. Fourth is TER, or translation edit rate, another measure of edit distance that is calculated as the number of total edits over the number of words in the reference sentence. Note that higher blue and WVCS scores indicate higher accuracy, but lower WER and TER scores indicate more accurate language models. Each metric is calculated for each pair of candidate and reference sentences and then averaged over all queries. Our algorithm was primarily tested on 92 sentences with words all part of SingularityNet's small world POC English corpus. For this purpose, we have used a corresponding small world link grammar dictionary, automatically inferred from high-quality link grammar parses created by SingularityNet's ULL pipeline, containing 42 total words and 5 total word clusters. Here are the meanings of our architecture-specific metrics. Single correct generated sentence is the number of times the algorithm generates a single candidate sentence that exactly matches the reference sentence. Multiple sentences with 1 correct is the number of times the algorithm generates multiple candidate sentences, one of which exactly matches the reference sentence. Multiple sentences with none correct is the number of times the algorithm generates multiple candidate sentences, none of which exactly match the reference. And no generated sentences is the number of times the algorithm fails to generate a candidate sentence. Too many results is when the algorithm generates over 25 candidate sentences. And finally, accuracy is the proportion of results within the categories single correct generated sentence and multiple sentences with 1 correct. The table to the left shows our NLG architecture's results when tested with the small world link grammar dictionary. The table on the right shows the results when tested on the same corpus, but using the complete LG dictionary. The decreased value of the single correct generated sentence metric and increased value of the multiple sentences with 1 correct metric are all direct results of the increased grammatical and semantic ambiguity caused by using link grammar instead of SingularityNet's small world grammar. Since the small world grammar was created from the small world corpus itself, each of the words in the corpus contains no other grammatical or semantic contexts, and thus no other sets of grammatical rules, besides those required to form the 92 sentences that the algorithm was tested on. However, since the link grammar database is much larger and contains many more sentences for each word, there is a greater number of valid sentences that can be constructed from those words, thereby causing a majority of reference sentences previously associated with a single candidate sentence in the first test to instead correspond with several candidate sentences in the second test. Our NLG architecture was also tested on 54 sentences, part of Charles Kaler's production of Lucy Maud Montgomery's Anne's House of Dreams, as found in the Gutenberg Children corpus, and performed as shown in the first table. Here, the decreased blue and word-to-vec cosine similarity as well as increased WER and TER, are due to the increase in results satisfying the multiple sentences with one correct metric. Not only is the proportion of results in this category greater, but the number of candidate sentences generated for each reference sentence is also much greater due to longer average sentence length and increased number of sentences per word used in the Gutenberg children corpus, resulting in lower average similarity scores and greater average error and edit distances. As shown in the table to the right, our NLG architecture outperforms prior work. As a baseline, we implemented a slightly modified version of a state-of-the-art transformer model designed for the task of sentence reconstruction from randomly shuffled sets of tokens, which exactly matches the surface realization task that our NLG algorithm accomplishes. The implemented transformer, which is built upon Spacey's English grammar, differs from the implementation proposed in the reference at the bottom of the slide, in that it uses a learned positional encoding rather than a static one. Label smoothing is not utilized, and a standard atom optimizer with a static learning rate is used instead of one with warm-up and cooldown steps. The reason for making these changes is that the modified transformer closely matches the majority of current transformer variants, such as bidirectional encoder representations from transformers or BERT. This baseline implementation achieved the results shown in the table to the right when tested on the Small World POC English corpus and Anne's House of Dreams, the excerpt of the Gutenberg children corpus. Overall, we can see that our NLG architecture, when using complete linked grammar and when using Singularity Net's ULL generated grammar for the POC English corpus, far outperformed the baseline model in terms of BLEU, War-to-Vec cosine similarity, and TER. It achieves a competitive WER score on the POC English corpus when using complete linked grammar, and a far superior WER on the POC English corpus when using ULL generated grammar, and on the Gutenberg children corpus with complete linked grammar. Overall, we find that our architecture outperforms the transformer, a ubiquitous state-of-the-art NLG model, and achieves stronger results across the board. So we've successfully created an unsupervised and interpretable model for NLG that still beats state-of-the-art generation models. So our NLS architecture can primarily be applied to the semantic query execution component of the question answering pipeline. One such scenario is the Aigents social media intelligence platform. Currently, the Aigents framework only handles written text in the form of oversimplified pidgin English. Our NLS algorithm can enable Aigents to support question answering from spoken audio input transcribed by STT, as well as extract information from crawled web pages to answer such questions. Next is text simplification, which is the process of enhancing a corpus of human readable text as to simplify the grammar and structure of the text while maintaining the original meaning. For instance, consider the unclear sentence, "Mom saw dad, who saw mom sawing." The text would be much simpler if split into the following three sentences: Mom saw dad, dad saw mom, and mom was sawing. Our segmentation algorithm can be extended to perform text simplification, thereby improving the quality of corpora that would otherwise contain vocabulary and complex sentence constructions not easily processed via computational means. More generally, our architecture can be applied to any NLP algorithms that operate at the sentential level, including automatic summarization, entity extraction, which is identifying and classifying important elements of a text into predefined categories, and sentiment identification, which involves extracting emotions and opinions presented in a text. Our NLG architecture can also be integrated into the Aigents platform to improve its question answering capabilities and thereby provide GCI to Aigents chatbots. In fact, if you're interested, I would recommend you watch our AGI 21 paper presentation on unsupervised context-driven question answering based on linked grammar, which outlines our most recent work to perform complete question answering. So anyway, with regards to NLG's applications, another prominent subdomain of question answering in which our NLG architecture can be utilized is that of virtual assistant AI technologies, such as Alexa and Google Home. Our NLG system, if integrated into these technologies in conjunction with the other parts of the question answering pipeline, would serve as an understandable and unsupervised rather than black box NLP framework. Our further work will be dedicated to, first, implementing grammatical and semantic disambiguation based on the context of a sentence or body of text, which we actually talk about in the context-driven question answering paper if you're interested. And two, extending the algorithm's generation capabilities to languages other than English, including those that require heavy morphology uses, such as Russian. So now for the final part of this presentation, code usage and demos. This is where it gets fun because all the theory I've talked about so far is super informative, but the real utility comes in using these algorithms for yourselves, testing them out, and potentially integrating them into your own architectures as an interpretable NLP backend. So let's start with the loader. Here are the steps for running unit tests. And here are the steps for getting the rule of your own input word. And I'll get into what that actually returns to you in a second when we walk through the entire GitHub repository. For NLS, here are the steps for testing the POC English corpus, then on the Gutenberg corpus, and finally, what's most useful and important, the steps for testing on your own sentences. For NLG, we have very similar instructions, so we can test on the POC English corpus, the Gutenberg children corpus, or on your own text. Okay, so now let's walk through the GitHub repository. Okay, so the first thing I want to go through is the README. So if you're ever interested in using these technologies after this workshop for your own projects, it's really useful to understand what exactly is in this repository. So first, as you can see, the first place you want to go to is this usage section because it has instructions for running different tests for each of these different tasks. So question answering, you don't need to worry about that for now, but if you're interested, that is our most recent work and our paper for the AGI 21 conference, but we can go straight to the loader. So the loader, as we talked about, is the utility infrastructure for NLS and NLG and question answering as well. So to test loader, which is the loader.java file, which I'll get to in a second, you have two options, either to run unit tests, like we talked about on the slide, or to run with your own word. And here's where it's really important. So this is the script that you want to use to understand the disjuncts and rules for the word of your preference. It'll output the rule and disjuncts associated with the word passed in as a second argument, so board in this line, given the dictionary path specified in the first argument. So note that n/4.0.dict just means the complete English link grammar dictionary. You can also try it out with Russian, but that's something we're still working on, so it's still very much in a sort of beta phase. And to test with a small grammar dictionary, you can use the full ULL generated dictionary path, which is shown here. Okay, then we can go to small world NLG. So this is exactly the same as the generator, which I'll get to in a second, but just for the ULL generated small world grammar. So that's this file name if you ever want to try this out. Okay, then we get to the generator, and this is where it gets really interesting. So first, you can run a series of unit tests. Then you can test on the Gutenberg corpus or the POC English corpus. But most importantly, you can use this script to test on your own sentences. For example, if you want to generate sentences from cake is now food as the words, you just plug that in along with the dictionary, so the complete English link grammar dictionary, and it'll output the appropriate sentences. So cake is now a food, for example, or depending on the semantic disambiguation, possibly food is now cake, even though we know that's contextually wrong. So that's how you use the generator. Now on to segment. So segment is very similar. Besides the unit tests and the test on the different corpora, you can plug in your own text. For example, you could just plug in the exact output you get from an STT engine right here. And it will first create a dictionary object using the loader given this dictionary path, and then it'll perform NLS on all the words or the token stream that you've plugged in to the model. Okay, so now for the next few minutes, I'll just go through the actual code that we have and how it works, how you can understand it and look through it, and then we'll open it up to questions. Okay, so first, of course, you want to start by looking at the data. So we have two folders, English and Russian, but focus on English for now. So within the English folder, you'll see that there are a lot of files. There are three things I want you to sort of pay attention to. First is the README. So the README, note this is taken exactly from the link grammar GitHub. So opencog/link grammar is the entire link grammar repository that you can look at for more details about the link grammar model, the dictionaries, things like that. But essentially, we take the files that are necessary to us, and this README describes how they're structured. So essentially, you have this 4.0.dict file, which is the main dictionary file. And as you can see, it has several different clusters. So first it defines the macros. So this is an example of the macro I was talking about. if you see clause anywhere in the rest of the link grammar dictionary, it's just shorthand for this entire link grammar expression. So now when you see their really big connector expressions, you can see why macros are so useful, because they provide really helpful shorthand and allow link grammar to be more readable than it currently is. Okay, so after defining the macros, it then goes to the words and their appropriate rules. So we can see, let's take this line. So n/words/entities.gods has these rules. So this is the connector expression, which is basically a set of different macros. So the marker entity macro, or given names macro, or directive opener macro, or directive subject macro. So essentially what it's doing is it's assigning that rule to every word in what we call a word cluster. So, and the word cluster is entities.gods. So if we go back out to this N folder, we'll see that words is this subfolder and it has different clusters shown here. So if we go to entities.gods, we'll see that this is a list of all the gods that have all the words that correspond to that big connector expression we just saw in the dictionary file. So for example, Eros, God, Hades, all of those words would be assigned those same rules corresponding to entities.god. So that's the benefit of word clusters. You can assign rules to multiple different words at once. Okay, that is basically all you need to know for the data. Now to get into the code. Okay, so we want to go into source, and test has a bunch of different unit tests, so you can look at that in your own time. But what we're really going to focus on is the actual architecture files. So that's going to go in the NLP folder. So here there are two options: LG or link grammar, and gen or generation, which also contains segmentation, QA, and so on. So we'll start with link grammar. So as you can see, it has the 5 main classes that we need to know. The loader that creates the dictionary object, which contains rules, words, and disjuncts. So we can start by looking at the dictionary. So this is a very simple class, and it's really helpful for you guys to understand what this does, because this is the basis of storing link grammar in sort of the backend for all our other models to use. So it's really nice that this is just simple code that you can understand, one Java class for the dictionary. So you can construct the dictionary either with the list of words that you already have, or just create an empty dictionary and add words over time. And that's why this is really useful, because a human linguist or the ULL pipeline can keep adding more elements, more words, and more information to link grammar over time. Then within the dictionary class, you can update words, get the rule for a word. You can also get the subscript for a word, and subscript represents the part of speech. So things like noun, verb, etc. So this is something that link grammar provides, but we actually don't use it at all in creating in NLG and NLS. But it is available if you need it for your task. And then you can get the words and so on. So an actual rule object, for example, it contains words that the rule applies to and the disjuncts that define the rule. And you have similar functions to update and add disjuncts and words that the rule corresponds to. Then the word, of course, is just a word with a subscript and the rule that defines it. Those are all the parameters that you have in a word. So once again, very nice and simple. And this word object is the class you use to create the list of words that are all in the dictionary. And finally, you have the loader. So this is a bit more complex, but essentially all it does is, if we go to the build lgdict function, it essentially takes the path to that 4.0.dict file and creates the dictionary object with the list of words within it. Okay, so now going to the generation part, we see that there are several different files. The ones we're going to focus on are generator and segment. So first, the generator, there are a few main functions that are really important. So let's go to first the generate sentence function. So what generate sentence does is it takes this array of tokens that are completely unordered, and the goal of NLG is to essentially order it to create a grammatically valid sentence. So what we do is we check several different orderings of that initial array of elements. Remember, with initial checks satisfying the planarity and connectivity meta rules, and we pass each ordering to the isValid function. So isValid then checks if a specific input array is grammatically valid or not. And to do that, that's where where is valid checks different pairs of tokens or groups of tokens and so on, and passes each group to the connects function. And the connects function, as you can recall from the presentation, is what determines if two or more words can be connected via connectable disjuncts. So last thing I'll go into is segment. And once again, it's very similar to generator. First, you have the segment function, which essentially checks different sentence boundaries that are possible within the initial ordering of words you're given. And for each possible sentence created by a sentence boundary you're checking, it goes to, once again, the isValid function, which checks if that ordering or that sentence you've created is grammatically valid, once again, using the connects function. Okay, that is all I have. Last thing I'll say is here are QR codes to our code, so that GitHub repository we were just going through, and our papers for NLG and NLS, as well as a contact QR code. If you ever want to email me or the other workshop organizers in the future with more questions, you're more than welcome to. And with that, I'll open it up to questions for the next 10-15 minutes or so.